Thank you. I'm going to move on to the next presentation. So I'd like to welcome Dr. Melanie Zeilinger, who's a professor at ETH Zurich. Dr. Zeilinger's research focuses on learning-based control and distributed control optimization with applications to robotics. And she's leading the Intelligent Controlled Systems group at the Institute for Dynamical Systems and Control. And she's going to talk about safe learning-based control today. So welcome.
Sorry, thank you so much for the kind introduction. The screen sharing failed. Let's start that again. 1 second. I'm not entirely sure. All right, here we are. So thanks again for the kind introduction and for the invitation to speak here today and for putting together this really nice workshop. So the question of how we bring together control and learning in a safe manner that we're addressing in this workshop is one that we've also been thinking about a lot in our research, and in particular, how we can make use of model predictive control ideas to create safe learning-based methods. And I'd like to present some of these ideas here today, and in particular, the things that I'll be presenting are work done by my PhD student, Kim Babersich. So when we're thinking about safe learning-based control, then really we're facing this fundamental challenge that if we want to learn in the real system, then we have to operate the system in the first place, that we have to apply actions in order to collect data. But of course, we know that every action that we're applying can already be a safety critical one. So the goal that we're facing is that we do want to allow a learning and potentially start with little information, but we want to ensure that certain safety properties are going to be satisfied at all times. Now, let me specify what we mean by safety. Of course, there's many different ways to define it. We're going to think about it in a rather general way of specifying a set of safety constraints that here denote with X, and we want those constraints to be satisfied. And you can also think about this as a slightly more practical definition, and you want these constraints to be satisfied with a certain probability. Constraints can, of course, be certain boundaries when you think about driving or flying a vehicle. And when you think about flying the vehicle just in 1D up and down, then we can draw the constraints in the state space. We want to be between floor and ceiling. And now when we talk about safety, we actually have to be a little bit more specific. And we mean constraint satisfaction, not only now at one time point, but for all times when we're operating it. And that actually for a dynamical system means that it's usually not the entire domain between the constraints, but a smaller domain in which we know we're not only safe now, but we can also satisfy constraints in the future. So one of the key methods to address constraints and control is model predictive control, a very well-established technique. Here I wrote down a nominal MPC formulation. So we write the problem as a finite time optimal control problem, minimizing the sum of stage costs using a model to predict going forward. And that allows us to directly impose those safety constraints, but also actuator limitations. Now, this is usually implemented in a receding horizon fashion, meaning that we only ever apply the first input and then repeat this problem and recompute it again for the next state. Because we solve a finite horizon problem, it's a common practice that we approximate what we're missing to infinity or to the end of the task with a cost to go here, but also with this particular so-called terminal constraint on the last predicted state of the sequence. The theory of this is very well established, if we choose these components appropriately, we can prove constraint satisfaction, stability, etc. The challenge often with defining a problem in an MPC type fashion is, of course, we need a sufficiently descriptive model But it's not only about the dynamics model, but also about the objective model, which is often challenging. Just to describe mathematically what we want from the system, for example, the performance may be very individual, but also we know that the controller properties directly rely on how we specify this objective. It has to have certain properties. And it's often not suited for very long-term objectives. It gets very expensive to do long predictions, or if we have very sparse reward just at the end of the task. So now all of this motivates using learning in model predictive control, and in particular learning for the dynamics model has been considered a lot and researched over the past years. There's many nice results from different groups. I just put down 2 results from our own group here, where we learn the model with the Gaussian process. Here I show 2 examples. One is for improving autonomous racing and the other for high precision tracking with a robot arm. So the performance of these techniques is really nice and very promising. But of course, what we also discovered is when you really have these very general and high performant learning-based models, then the theory gets very challenging. So what I'd like to discuss today is some ideas for how we can integrate learning in an MPC controller and provide a certain performance and safety analysis of that. And then in the second part of the talk, we'll be looking at how we can use model predictive control ideas to introduce constraint satisfaction properties for basically any learning-based control method that you want to apply. Okay, so let's begin with the first goal. We've already talked about learning the dynamics model, but also learning the objective. And here in the following, we'll consider a parametric model, and we're going to learn these parameters. But then we can also think about learning the optimal control solution in order to improve these infinite horizon components here, which will directly affect the performance of the MPC controller. And there's many different questions that we can ask. What I'd like to focus on is the question of how we efficiently collect the data, of course, then how we analyze performance and safety, and how we can leverage past data and potentially that may have constraint violations in them. Of course, the question of model uncertainty is not new in model predictive control. It's been classically considered in so-called robust MPC methods, where we assume a bound on the uncertainty and then get robust constraint tightening via constraint satisfaction via constraint tightening techniques. The difficulty is that we directly work with this uncertainty bound, and so we assume that we know this bound. And this can become restrictive when we think about learning, because we may have very large uncertainties where we haven't seen a lot of data. There's stochastic MPC techniques that allow for potentially unbounded uncertainties and allow for constraint violations or probabilistic constraints. Here, even though it's often perceived as being less restrictive, we do assume that the uncertainties are coming from a certain distribution that we know. And it gets more difficult to give closed loop constraint satisfaction guarantees. Now, we've looked at this for a while now, and for at least for linear systems, we were able to recover some of these properties. And then there's soft constrained MPC, something that's potentially overlooked a little bit, but always done in practice. And what it does is we have to ensure that this optimization problem that we need to solve at every time step remains feasible to get some control input. And so here in soft constrained MPC, we achieve this by relaxing the constraints. That allows us to deal with single large disturbances, unforeseen events, really the unknown unknowns, or infeasible initial conditions. The difficulty here is that it then becomes more challenging to say anything about stability guarantees. And we've looked at this a bit in the past, and I'll present one approach now or later, which allows us to still provide stability properties in such a setting. And in the following, I do want to focus on this practical setting of soft constrained FPC. Okay, so let's begin with learning the objective or the dynamics model. And here we've looked at the question of efficiently collecting data, and that's basically the question of active learning. So it can be really beneficial to think about which information you should be collecting to maximize performance. Now, if you do that really online, that brings you to the problem of dual control. It's a very nice review paper on that. It's a hard problem. We've looked a bit into approximating this, so getting an approximate dual MPC formulation. It gets a bit easier if you think about episodic learning, where Bayesian optimization type techniques address the exploration-exploitation trade-off. And here we looked at active learning of these problem parameters, focusing on addressing very high dimensional parameter spaces, but also the theoretical analysis, which is what I want to present now. In order to do this, we've actually worked with a very efficient and simple technique based on posterior or Thompson sampling. So we're again looking at this MPC problem, and we have these parameters here that we want to learn, but now we formulate the soft constrained MPC problem, which means that we're relaxing our constraints. If you think about these simple inequalities as your constraints, we would be adding slack variables to them. And then you penalize those slack variables in the cost to get minimal constraint violation. And it's well known that if you have a high enough penalty here, then you get a so-called exact penalty function. So you can ensure constraint satisfaction whenever that is possible. And the goal is that we like to learn these parameters in an episodic fashion. So we always run the MPC controller, compute the closed loop cost, so improve then the parameter based on that data, and continue. And what we want to see is if we can analyze the performance and safety of the scheme. As I said, here we worked with posterior sampling. Let's just briefly go through how that works. We start with the prior distribution of our parameters and this parametric model of the dynamics and the objective. We start with 0 data. So at the beginning, we just sample from our prior distribution. At the beginning, we're going to have a lot of uncertainty, so that naturally leads to exploration. Then we apply the MPC controller with that parameter, compute the closed loop cost, and extend the data set and sample again from the next posterior distribution. So if you continue to do that, the parameters start to accumulate, at least the task relevant parameters start to accumulate around the true parameters. And so naturally we start exploiting. This works extremely well in practice. Here are just 2 small examples. In one, we look at a thermal example. So 100 thermal units that we have to control. We have a maximum temperature limit and some uncertainty efficiency here. And a little drone search example where we have a drone which has to go to some uncertain position. There's uncertain wind, dynamics are uncertain, and we have a maximum range of this drone. And then now we compare this approach that I presented that we call Bayesian MPC against doing what we call posterior nominal MPC, where you always take the mean estimate of your posterior distribution and then apply the MPC with that. And what we see is that this approach with posterior sampling performs much better in terms of the cumulative regret, meaning the difference of the closed loop cost of the applied policy and the policies of the MPC knowing the true parameters. So we not only get faster convergence, but overall also less variance in these examples, and really achieve very, very nice performance, even though the approach is so simple. Moreover, the nice thing is that there is a strong analysis that comes with these techniques, and we were able to show that we can extend the results derived for reinforcement learning and unconstrained techniques also now to this MPC setting, and show that the sublinear bound on the expected cumulative regret also holds here. Basically, what we need to show is that our expected closed loop cost is still Lipschitz continuous. And that is in particular true if you have linear dynamics, a strictly convex cost, polytopic constraints, but under more slightly stronger assumptions, you can also do that for nonlinear systems. So we do get a performance guarantee. Now we were wondering if you can say anything about the safety properties of doing this. And it's clear that in this simple setting here, when we just sample these parameters and run the MPC, this may lead to constraint violations. But we were wondering if we can analyze and bound the number of unsafe learning episodes that we're going to see. And in fact, we can. What we need to do is in this closed loop value function that we're analyzing, we're integrating the slack penalty. And then in addition to just softening the constraints, we're also applying a progressive constraint tightening, so basically a tightening that grows over the horizon, just a little bit. The intuition is that this gives us a bit of wiggle room before we violate the constraints. And by looking at this setting, we can then show that there actually exists a lower bound on the slack penalty scaling such that we can bound the number of unsafe learning episodes, the expected unsafe learning episodes, by the cumulative regret. So if that is a sublinear, if you have a sublinear bound on that, then the ratio of the number of unsafe learning episodes versus the total number of episodes vanishes, which means that we're not going to see any unsafe learning episodes anymore. So this is really just the first step and towards combined analysis of performance and safety. And we believe that there's a lot of potential going into these directions for analyzing performance and safety together. Okay, so in addition to learning now the model, we wanted to look at these infinite horizon components to improve the controller properties. Now, just briefly to recap, so the idea is that with these components, we're approximating what we're missing by looking at only the finite horizon to the end of the task horizon. So here for the cost, that means that we're usually approximating the cost tail by rolling out some suboptimal control law. And for the constraint, it means that we're defining some set in which we know there exists a control law that will keep us inside of the set going forward. Now, the Francesco Borelli's group has proposed a nice way of constructing these components based on previous trajectories. The idea is basically in a simple presentation that you construct such a terminal set as a convex hull of your available trajectories. And you also use the cost to go from these trajectories and then combine it into a new terminal cost for your last state. So that works very well. However, the assumption is that the trajectories that you're using, they must already satisfy your constraints. And moreover, of course, even though there are robust extensions of this, you may run into infeasibilities if you see unexpected disturbances. So you may be wondering why we're worried about not being able to use trajectories that violate the constraints. Well, very often you're running your system in different scenarios in training episodes and you're collecting the data. And there you may have a looser set of constraints than you have at runtime when you really want to impose more stringent safety conditions. So for example, think about training a car on a test track, but then when you go on the real racing track, then you have more tight constraints. So what we want to do is also leverage these trajectories with potential constraint violations and ensure feasibility of that problem. And we do that by using a soft constraint extension. Here, we work with a particular soft constraint formulation, which gives us very nice theoretical properties. The idea is that you compute a terminal set that only respects input constraints. So you neglect state constraints entirely. And then we define a slack variable for the last state of the sequence in a very specific way. So we define a scaled terminal set such that the last state is just contained, and then the slack variable to contain the scale terminal set. So here, for example, our last state would be such that we cannot really scale down the terminal set. So our slack has to be such that the entire set is contained. But if we can move the terminal state inside, then we can scale down our terminal set and reduce the slack. Then we impose that terminal slack, and in addition, relax the constraints further if we need to over the prediction horizon. We do something similar also for the cost. So we can now also use scaled cost data using the same scaling. The nice thing about this particular soft constraint formulation is that we do get stability guarantees. And we can also show input to state stability for uncertain systems. We were able to write this different from our previous results and as a convex optimization problem for linear systems, also when you work with polytopic constraints on all the constraint sets. Of course, you get now also an enlarged feasible region of the problem that you're running because you work with soft constraints. And if you replace trajectories that have constraint violations subsequently as you're running the system with new trajectories that don't have constraint violations, then you can leverage the available theory to show that you're converging to the optimal controller. So here we've done that again for the same little thermal example. We run 10 episodes, and the predicted cost by iteratively improving now these terminal components converges to the cost, the closed loop optimal cost. So this was looking at how to integrate learning in an MPC. And when you can write your problem in that way, that really works extremely well. It can, however, as we discussed at the beginning, sometimes be difficult to write the problem in this way. You may not be able to formulate your objective in a nice way for numerical optimization. Maybe you need a very long horizon for prediction. Active learning is still very challenging. And in all these instances, you may want to use a different learning-based controller. And what you can still do is use the MPC just for the constraint satisfaction. So the idea is that we want to define this in a modular way. We call this a safety filter, which is agnostic of the controller that you have here. It just gets the proposed input that you want to apply to your system. Verifies if you can safely apply that input while remaining safe going forward. And then you can apply the input. And if that's not the case, and you would be violating constraints in the future, then you have to propose, of course, an alternative input to remain safe. Now we can write this in a model predictive control type fashion using similar concepts by saying, well, the state is actually now safe if we can plan a forward trajectory to some more conservative domain in which we know a controller that always works. So a proposed input is safe if it leads us to such a safe state from which a trajectory exists. So it really comes down to a forward planning problem. There's a bunch of related work which look at similar predictive ideas, and of course also based on other concepts. I think Claire is going to present some ideas of such safety filters based on reachability analysis, and maybe Aaron on using control barrier functions. So there's several other nice techniques that you can use. The benefit of using this MPC approach is really that it allows us to leverage this entire back end of MPC methods that we have available. And it allows us to scale this to rather complex systems. And the reason is that this really comes down to solving an optimization problem again for computing this forward trajectory. So why does it keep us safe? If we have a learning input that was safe, so if we're able to find such a trajectory, and then we've proposed another learning input that's unsafe, we do have this trajectory available. However, we can also just optimize over this first input and say, well, ideally, we want to make the first input equal to the learning input. But if we can't, give us the best one that's closest in a certain sense, such that we can still find a safe forward trajectory. So we get in one problem really the verification of a proposed input is safe, but also the computation of the backup controller. And as I said, we can now leverage all the efficient solvers that we have available for MPC. So this has many benefits. Of course, we don't really get around the model. So that challenge still remains. But it's important to keep in mind that it's now different than what I discussed in the first part of the talk, because now the model is not directly, that we're using in this MPC context, it's not directly responsible for the performance of the overall controller, but it's mainly used for the constraint satisfaction. So here we thought about many different variants of model assumptions that we can use: robust, stochastic, distributed. And I just want to present one idea to make robust techniques more practical in this setting. So what we would do, applying a robust technique, again, to address the fact that we may have learned some dynamics model, but there's still uncertainty about it, is that we would lump all this uncertainty in one term and then construct a uniform error bound over it. So a bound that holds everywhere. And then we would deal with this maximum error. There's today many nice methods also for nonlinear systems for how to do robust MPC. However, the challenge really comes from this uniform bound, which can be conservative if you think about a learning setting where you may have really high prediction uncertainty in some domains, even though you're fairly certain about the model in others. So the idea that we had here is that you can really turn this problem around and rather say, well, I specify a certain model error that I'm willing to tolerate, and then I restrict my planning to a subset in which I'm sufficiently confident. And the key is that, again, we never want to explicitly compute that set in which we're sufficiently confident, but we want an implicit formulation. We were able to write this by describing basically a state and input dependent error bound on the uncertainty, and then imposing that this error bound has to be contained in our maximum error set. I don't want to go into the details, but looking at a Bayesian regression setting, you can actually write this constraint in a very simple way as a bound on your posterior variance. And so the nice thing is really that you first decide about a constraint tightening, about an uncertainty bound, and then if you're initially feasible, you again get your safety certificate by running this scheme. Okay, I just briefly want to present an application. We applied the safety filter idea to small scale autonomous race cars. Here we first see the safety filter applied to keep the human driver safe. First, the human driver is doing a very good job in keeping the car safe, so there's minimal intervention. But then when the driver is doing a bad job, basically not steering at all, the safety filter has to kick in and overrides the commands a lot in order to keep the system on track. Here, we're learning a policy from an expert and apply the safety filter to remain safe while doing that. So here we have the first iteration. Policy is not very good yet, so we need the safety filter to keep us safe. And then if we continue doing that over a few iterations, then we see that our safety filter doesn't have to really intervene anymore. So we can really safely learn these policies. Okay, with that, I'd like to sum up. So I think there is really a lot of potential for integrating learning in controllers to improve the performance, but also design cycles, etc. I've presented a few ideas for integrating learning in an MPC for the models, and in particular, a sampling-based approach where we're then also able to get a performance and safety analysis, but also to learn these terminal components from trajectories, also with constraint violations using soft constraint techniques. And then we looked at this modular safety filter with MPC, which really has the benefit that we can leverage all these tools and get a very scalable approach. But I do think we have to address more going forward is overall really think about a combined performance and safety analysis. We tend to do safety, but forget a little bit about the performance analysis. We have to think about how to efficiently collect and use data. And also when doing all of this, that these things have to run in real time at the end of the day. So real-time computation is an important topic. Let me just thank the team again and point out that if you're interested in these things, there's the Learning for Dynamics and Control conference happening on Monday and Tuesday next week. The registration is closed, but you can watch all the oral presentations freely on YouTube. So we're looking forward to seeing you there.
Thank you very much, Melanie, for a really exciting talk. Are there any questions from the audience? Feel free to raise your hand or ask in the chat. Or if you're already in the speaker list, you can speak directly. I have a question while others are thinking. I was thinking about the Bayesian MPC, which you talked about in the beginning. I'm curious, you mentioned you compute the posterior distribution over the parameters. How is this done? And was it done by Gaussian processes in that case? Or is it, how is it done in general, I guess?
Yeah, so we just applied linear Bayesian regression in this case. Yes, so much simpler actually.
So do you think I imagine this is an important component. So as we start thinking about more complex models for either the controller or the system dynamics, do you see this being an important problem for kind of predicting uncertainty for the parameters in addition to the parameters themselves?
Well, yeah, so for the Gaussian processes, that really becomes a limitation for predicting the uncertainties. The nice thing in this, what I presented is that we're not predicting the uncertainties. We're just sampling a parameter and then we're running the MPC controller as if that was the true parameter. And so the MPC doesn't become any more expensive. Whereas if you're propagating all your uncertainties, that really requires a lot of effort to get this in real time.
Thank you. Any other questions?
Can I ask one? So is it not possible to include the soft constraint you said in the input as an input constraint as well?
So absolutely, you could do the soft constraints on the inputs. However, input constraints are usually considered hard because that's an actuator limitation that you often just have no way of getting around, right? That's your limitation of your maximum thrust or whatever you have, which is why generally these are not softened in practice, but you could if you wanted to.
So technically it's possible, but maybe
yes,
there's no requirement.
Yes. Well, when you're then going to the real system, there will be a limit on the inputs that you can apply, right? And if you relax your inputs and you get all the nice properties, in practice, you're going to lose them again because you're dealing with inputs that you can't apply in practice.
I see. Got it. Thank you.
Thank you very much, Melanie, again. I think
Thank you so